Hi everyone. So welcome to our enrichment seminar, the first one for this fifth grade year of free Asian math. What we will do, but first of all, let's emphasize this is tentative. We haven't decided whether we will continue this for every week. It really depends on how much interest we receive from all of you. If you think that this Saturday seminar, which is a 90-minute program, we will spend 30 minutes on discussing some of the more challenging homework problems in the week, then spend the next 60 minutes to discuss some more advanced, more interesting mathematical stuff that will not be taught in any public school. If you think this seminar will be interesting and helpful, and you want to opt in, and if we have enough people wanting it, then we will continue. If there's no sufficient interest, then after the first 2 weeks, we will stop. Okay, so I hope you will find this helpful and interesting. This is the first one because we just get started. We actually, because of the timing, because we have regular lectures on Wednesdays and Fridays, so it's unlikely, actually it's impossible for we to discuss the Friday homework. By the way, yesterday homework hasn't been posted yet, but you will get it tonight. So it won't be possible to discuss Friday's homework on Saturday. So what we will discuss would be the Wednesday homework of the same week and the Friday homework from the previous week. So that's what we're gonna do to spend the first 30 minutes. We just got started. So let's take a look of some of the more interesting homework problems from this week. So this is the first one. This is exercise 5.66006. By the way I number those problems is that you got a major digit here is 5, meaning that this is a grade 5 homework problem. I plan to give you 10 homework problem every lecture. So if for this year, we'll have 30 weeks, 60 lectures. So that should be 600 problems. That's how I number those problems. I do intend to make a video solutions later on and post them on the internet. But because this is the first year, I simply do not have the bandwidth to do that. All right, so let's jump into this problem. What is this problem? So you are given some sequences, right? You want to identify a certain pattern within the sequence so that you will be able to fill in some blank, which means some missing number of numbers in the sequence. Of course, the numbers you filled in must follow the same pattern, so don't break that pattern. You need to make it consistent. There are two problems in this, two sub-problems in this problem. So let's work on the first one. Well, let's emphasize a little bit. There are some actual follow-up questions. For example, in this one, there's can you think of a way to state it in the mathematical language question? This one has actually 2 asterisks, meaning that it's a very challenging problem for you to do. So any questions or portions of the problem that has at least 1 asterisk, it's optional, meaning that it's quite challenging. Because free Asian math really aims to provide a good, fair math education to anyone in the nation without assuming the student's family background, academic background. So we do want to cover almost all students, no matter where you're coming from. So it wouldn't be fair to throw some really challenging competition math level problem to everyone. So those problems are actually optional. But if you really like math or want to do math well, I think it's worthwhile for you to work on those problems. That's why you see that you have 2 asterisks there. By the way, the solutions have already been posted in Google Classroom. You should be able to read the solutions, but it will be more helpful if we have an in-person explanation of those problems. Okay, so the key for a problem like this is that you have to be very careful when observing or reading the numbers to see what is going on. What is a pattern? A pattern means that there are certain relationships within those numbers. They are not randomly chosen. They are not independent of each other. They are correlated to each other in some way. The correlation can be fairly simple or it can be very complicated. But usually when the problems like this are given to you, it's somewhere in between. The easiest, for example, we already did that. If you have a sequence like 2, 4, 6, 8, this is a very simple relationship, right? You can easily see that every time you get a new number, you get that 2 more. Actually, if you have this sequence, if you divide every number by 2, what happens? You simply get the most easiest sequence that is just the natural numbers. Of course, we did not include 0 there, but essentially, this is natural numbers. So the pattern here is really trivial, but it can be expanded into some fairly difficult problem. So what is the pattern in the first sequence here? If you really take a long look, you will be able to see that every number in this sequence, say 5, by every number we mean starting with the third one actually. Every number here, like 5 or 8, it's the really sum of the 2 preceding numbers. So what are before 5? You have 2 and 3, right? So 5 really is 2 plus 3. And 8 is 3 plus 5. How about 3 itself? 3 is actually 1 plus 2. Because you need 2 preceding numbers before each number, so if this is the definition of each number, then we cannot possibly define the very first one and the very second one, because they do not have sufficient preceding numbers. We need at least 2 preceding numbers. That means that if we have a definition like this, we can only start with the very third one to well define every number. But from that point on, every number can be properly defined. So we need 2 numbers as starting point. So in this example, the first one, we have 1 and 1. And you can see that the very third number, which is 2, 2 equals to 1 plus 1, right? So from that point on, you can see that we can define every number in this way. Okay, so this is the pattern we identify verbally via English. So if that's the case, what's the first blank? You'll see that first blank is right after 5 plus 8, 5 and 8, so this number should be 13. Okay, 13 should be here. And does that make sense? You can check whether this will be consistent with the general pattern. If this is 13, what will be the next one? Next one would be 8 plus 13, which is 21. Bingo, that's exactly what is there. So we are confident we did the right thing. All right? So with 21 there, what is the next one? Without any doubt, that one would be 13 plus 21. So we get 34. Okay? So this will be 34, and this would be 13. Okay, very good. So the problem is kind of just not too difficult, but not too trivial. All right, now how about the next problem? If you just pay a little bit more attention, you will see that the pattern here actually is exactly the same, in the sense that starting with the third number, which is 3 here, every number is just the sum of its 2 preceding numbers. For example, 3, let's switch to a different color. 3 equals to 2 plus 1. And the next one is 4. 4 equals to 1 plus 3, right? And 7 equals to 3 plus 4. That's exactly what we saw in the first example. But why all the numbers are different now? It's because its starting point, the two initial starting numbers are not exactly the same. In the first example, we have 1, 1. Now we have 2, 1. So you see just with a little bit twist, the whole sequence looks very different. And that's the beauty of mathematics, right? You think this is trivial, it will give you at least on its surface, the two sequences look very different. But regardless, identifying this pattern allow us to write down this one would be 4 plus 7, that's 11. We can actually, let's make sure that we be a little bit consistent. So this is 11 with a green color. And the next one, 18, is 18 the sum of the first, the preceding two? Yes. So 7 plus 11, that is 18. So then 11 plus 18, that will be 29. Okay, at this point, if you are just doing your homework, you're actually done. You don't have to work on the next much more challenging one. Can you think of a way to state it in the mathematical language? What do we mean by that? State this, what we just went through in the mathematical language. Well, the reason for this exercise is for you guys to build a good habit of reading mathematics, getting comfortable with mathematical notation. We just use English to describe the relationship, right? If you have to write that down, it can be a little bit verbose because, we have to describe a fairly just complicated relationship. Each number, starting with the third one, is the sum of two preceding one in a sequence. If every mathematical problem involves things like this, then quickly we will have to use complicated English to describe the situation. And that is never good because you are not taking the English class, right? This is just a very small problem. A more complicated problem you can imagine involves a lot of additional elements and information. So if you use English to describe the nature of the problem, describe all the relationship, then you will very easily write in something like a thesis. We don't want that. We want to describe everything in a pure mathematical way. To that, you inevitably have to use mathematical notation. And what we will use is very much the foundation of algebra. That is, we use symbolic notations to describe a mathematical problem. Okay? So, what do we mean by that? Now, we want to describe this relationship that each number, starting with the third one, in the mathematical number sequence, can be written as the sum of the two preceding numbers in the same sequence, right? To describe this relationship, we first need a way to represent this sequence of numbers. Because in general, a sequence numbers can be any kind of numbers. You just cannot possibly enumerate each possibility. So what do we do to generally represent a sequence of numbers? Well, you think about this. When you have a sequence, what is that? The first number, second number, third number, so on. You don't know, or you don't need to describe what numbers yet. But at the top level, you want to say there's a first number, there's a second number, there's a third number, and so on. What happened there? You essentially, there's a hidden or underlying sequence. 1, 2, 3, 4, right? if we add order, that is really first, second, third, and so on, fourth, so on. So this sequence really corresponds to the counting number sequence, which we, by the way, just studied yesterday. 1, 2, 3, 4, right? Now, we understand the sequence of numbers corresponds to such a counting number sequence. If we want to represent all of them, we better use symbols like A, B, C, D, E, right? But that does sound very promising because we only have 26 alphabets. We only have 26 letters in our alphabet. We will quickly run out of all of them, up to 26, right? What can we do? Do we add some arbitrary symbols like this, or even question mark to represent a number? That would be ridiculous. It looks silly. So what we'll do in algebra is a brilliant idea. Perhaps we just use one single symbol, that's just an A, to represent all of those numbers. But how can you use one symbol to represent many, many numbers, potentially 1 million, 1 billion? Well, that's exactly where this underlying counting number sequence comes to help. We can use the idea like we attach this underlying sequence as some so-called subscript to that one symbol A. So we say this A1, but we don't write it like A1 like this. We just put a smaller version of 1 like that. It's a tiny, tiny version of 1 put at the foot of this number A, or letter number A, and do the same for every other number in the sequence. So the first number we will denote it as A1, and the second number now still A, but with A2. That way we have a very kind of economic way. Just use A1, A2, A3, A4, and so on to represent as many numbers as you want, right? So this is the standard algebraic way to describe a number, a sequence of numbers. And this is very natural to understand. A1 is the first number, A2 is the second number in the sequence. And more interestingly, if we want to say, what is the X number in this sequence? We don't even know, or we don't need to specify what the value of X is. We generally want to say the X number in this sequence. Well, that notation would be just something like this, AX. Remember this, whatever value it is, it's simply a subscript telling you the position of this member or elements in the sequence. So X itself can represent any counting number. It just tells you this is the X elements, or sometimes you could member of this sequence. All right? So this is the very natural, very economical, very beautiful way to represent a sequence of numbers with a so-called symbolic notation. You have to get comfortable with this. I know everybody, nothing will be comfortable at the very beginning, right? Even you buy a very expensive pair of Air Jordan, just sneakers, $500, it may not be that comfortable when you just tried for the first day, right? Maybe after 1 or 2 weeks, it will break in well, but no matter how expensive it is, new shoes are usually a little bit uncomfortable, all right? So that's universally true. But don't worry, you will soon get comfortable with this. Now, equipped with this sequence of symbolic representation of numbers, we will be very easy to describe the relationship we saw earlier, okay? So what do we do to describe the relationship? We know one member, starting with the third one, will be written as the sum of the two preceding members. So let's just say we represent a member generally as AM. We can do that, but for a little bit just consistency with the homework solution, we will switch this to n plus 2. This doesn't really matter. It's just the shifting. You will understand what I'm talking about. Let's just say we are talking about the n plus 2th member of the sequence. Then, according to our discovery, it must be the sum of an plus an plus 1, right? Because if this is the n plus 2th, the two preceding members will be the nth member and the n plus 1 member. So this is just the relationship that we just discovered. However, in math, we have to be very careful and rigorous. We already say that this relationship or this definition is true only when starting with the third number. It doesn't apply to the very first one and the second one. So this has a constraint, and that comes to what number n can be, right? So the relationship, we just say that n plus 2 has to be at least 3. If you have already learned a little bit about inequality, you will see that it has to be at least 3. So greater than or equals to 3. That simply translated, we are jumping a little bit ahead of ourselves because we have not talked about inequality in free Asian math, but this is not terribly difficult to understand. So we will just explain it on the fly. What this can be simplified is if n plus 2 is at least as large as 3, then n has to be at least as large as 1. Okay? So because of this, the smallest one, an here, will be a1. And that's perfectly consistent with our understanding because that's the very first member in the sequence. So what we say here, the relationship is an plus 2 equals to an plus 1 with a constraint n has to be at least 1. Of course, the other underlying assumption is that n is an integer. That's just so obvious because whenever we talk about a sequence or subscript, everything is an integer or positive integer. Okay? You may actually later on have some weird notation. This can actually make negative, but that's very superficial. Okay? So in general, all those subscripts at least will be 0. We usually do not have negative subscripts. Okay? All right, so this is the relation we just described. But there's still one issue here. That is that we have not defined what the first and the second numbers or members in the sequence is, right? Well, because the problem only asks you to describe the pattern, those specific initial values are actually unimportant because that point is irrelevant in the sense that they are not themselves are not involved in this pattern. That's exactly why we have two very different sequences. They actually exhibit exactly the same pattern, but they do have different initial values. As the result, the two sequences look very different. Okay? So, if this is the homework or this is the exam problem, at this step, you are done. You don't have to say, what is A1, what is A2 in either sequences. That's not part of the pattern. For any initial two values, you can generate a sequence with this relationship. But what are those specific things here? Well, the first sequence is the so-called Fibonacci numbers. The second one is actually called Lucas numbers. They are closely related. And the Fibonacci numbers are just so fabulous, so important, and it has so many interesting properties. I think there's a mathematical academic journal exclusively dedicated to studying Fibonacci numbers. It's a wonder in the whole universe, Fibonacci numbers. And if you go to YouTube, you will find a lot of interesting videos regarding Fibonacci numbers. But today, we just try to use this to give you understanding how we should use notation, mathematical notation, to dramatically make our life easier when we discuss or work with mathematical problems, right? Isn't this simple notation beautiful? That's all you need to describe what we went through with complicated English. Okay? All right, so let's work on another problem from the homework. Where's my, oh, there we go. Okay, we will actually jump to this problem because I heard from some of your parents that some people feel this is difficult. Now with that notation idea under our belt, this problem is actually not that difficult. All you need is to take a long, hard look to find some relationship. By the way, a relationship can be very complicated and can be very simple, right? If the relationship, say, involves more than 2 or 3 numbers, say you have to observe 5 numbers in a row to describe a relationship, that's probably too difficult. Nobody can actually observe or identify such a relationship without any prior knowledge. But a trivial one like 1, 2, 3, 4, that's nothing. Everybody can tell. Even you are a kindergarten student, probably you can tell the relationship because it's trivial, right? For this one, it's somewhere in between. It's more toward the more difficult one. If you really compare 2 adjacent numbers, you cannot tell much at all. You can play it around, adding 2 adjacent numbers, subtracting one from the other one. Still, you have no idea what the relationship is. But if you look at 3 consecutive numbers here, like say 4, 11, 29. Okay. Is there any relationship there? The relationship is actually, that's how you usually try some trial and error kind of experiment to see what happened. If you plus 4 and 29, what will you get? You get 33, right? This is a number sense. What is 33? 33 is 3 times of 11. That looks very interesting. But does this generally apply to all the other ones? Let's try the next one. 11, 29. Oh, no wonder it's so small. Oops. Okay. This is a little bit too big, but I think we can work with it. So 11, 29, 76. With this as a guidance, we want to test whether the same relationship holds up. 11 plus 76, that's 87. 87 is exactly 3 times of 29. Bingo, this is 29 times 3. It holds up. So perhaps we can try one more. 29, 76, and 199. Yeah, the numbers becomes bigger, but luckily we are all mathematical genius, right? So no big deal. We can even beat an expensive calculator. So 29 plus 199, that's 228. By the way, there's some 228. There's some mental math technique for a problem like this. We will cover those trivial ones. So what is this? Is 228 3 times 76? Yep. If you know how to do that quickly, you will see that this is 228. By the way, how do we do this quickly? Well, there are multiple tricks for this, right? One thing is that for number sets, you really need to understand what Roll's multiple of 25 are. So 75 is actually 3 times 25. If you time that with another 3, you will be 225. Why this is relevant? Because 76 is just one bigger than 75, so we can do something like a distributive property, which we haven't discussed about, but we will in a few weeks. So this will give you 225 plus 3. You can easily get to 228. So once again, this relationship holds up. So now we can confidently tell what happened is that if you add the first number and the third number, that should be 3 times of the second number, which is 2, right? 1 plus 11, that's 12. 12 is 3 times 4. So now we know what is the deal, okay? So that means that in this case, you will need to add 199 with 1364, then divide this by 3. And that's how you will get the result, which is 521. Another way would be you work on 76, 199, and this, so that will be 199 times 3, that's triple of the middle one, then minus 76, right? That will also give you exactly the same number, because of course this must be the case because the problem was pre-verified as a valid problem for you. So either way, you'll figure out this is 521. All right? So we discussed this kind of technique, but how about the last question? Well, now we know what we need to do, right? We spent so much time on the Fibonacci numbers and the underlying concept. Now what is the relationship? Let's just say you have a number AM, and it has a succeeding sequence member, that is AM plus 1. It has a preceding one, AM minus 1, right? Remember, rows are the so-called subscript. It's just nothing but the index or the position of each member in the sequence. What is the relationship we just identified? We see that AM minus 1 plus AM plus 1, those two members, we add them up, this should be 3 times AM. Okay, so this is the relationship you identify. Well, with a little bit of manipulation, this involves equation, which again, we have not talked about, but it's not that difficult to see that now we can simply move this guy, subtracting this guy from both sides, minus AM minus 1. So subtracting this same guy, meaning that we will actually just take this away. So we can do something like this. AM plus 1 equals to 3 AM minus AM minus 1. Of course, this kind of relationship, you can always shift this a little bit. Say, make all the subscripts a little bit bigger so you can write exactly the same thing as AM plus 2. That's just one more. Then this one will correspondingly become AM plus 1, and this one will become AM. The constraint will actually be changed. So because you can see that a relationship like this, just like in the Fibonacci sequence case, you do need 2 preceding members. So this relationship only applies with the third one, right? So for the constraint, this would be M plus 1 at least 3. So that means that N has to be at least 2. Okay? If you write this way, then means that N will be at least be 1. They are the same. And in general, a relationship like this is called a recursive relationship. If any of you does some computer programming, whether it's Python or Java or C++, you should be familiar with this kind of recursion idea. All right? So that's so much so about homework. This is a 5:05 here in California. We are burning 5 more minutes than planned, but it's okay. We generally want to spend 30 minutes on homework. We will not be able to talk about every homework. That's why you have a solution to read. But for things like this, it's more like we want to discuss new concept, not necessarily more difficult, but those concepts have just a kind of a profound impact on your future study. We will not be reluctant to invest some of our time into that discussion. All right? So, that's the homework part. Now, we are ready to talk about our enrichment. Okay. So, what is the enrichment portion of our seminar about? It tries to give you something that you will not learn, certainly not from Common Core Math, which is, in my opinion, well, I don't want to put too many critiques on that system, but you really cannot learn much. And it will not be even in the regular free Asian math, meaning for this year, what we will discuss on Wednesdays and Fridays. Why? Because the general purpose of free Asian math is try to help as many students as possible in our nation, so we cannot really put too much burden on that big population. Because there's always some boundary where you just cannot expect every student to be an Albert Einstein, right? So that's just the fact. So there are certain materials or topics that will be a little bit too advanced for some just general population. So that's where we will discuss in this optional enrichment portion of our program. It's completely optional. Is this geared toward competition math? Yes and no. For the yes part, because the two do overlap a lot, there's no reason why we cannot take advantage of this enrichment study for the benefits of your competition math study, right? So they do overlap. But is competition math our sole purpose? Absolutely not. Even without doing any competition math, such enrichment should give you just broad training on how to become a more logical and smarter person. That's really the goal of all my program. I want to help young students to become a better thinker, more logical person, and more importantly, to hone your problem-solving skills. And that's not limited to mathematics. It can be actually any problem in your future career. All right? So let's take a look at what we'll study today, which is, I promise, will be fabulous. Okay? And this week and next week as well. So on your screen is a well-known problem that one of the greatest of all time mathematician, Carl Gauss, the legends say that he was able to work out this problem at a very young age. Some say age 10, some even say age 7. There's no just indisputable evidence, so I just assume when he was a young kid. He was able to solve this problem, 1 plus 2 plus 3 plus 4, all the way to 100. Because this problem nowadays has become such a very, very basic training problem. So a lot of kids learn this when they are in grade 1. It's not a big deal for you to, but there's a big difference because even you know how to do it, you were taught to do this. Gauss, at that time, about 400 years ago, let me see, yeah, probably a little bit less than 400, but 300, somewhere between 300, 400 years ago, he was able to do this, figure it out all by himself. And that time, all the mathematics we know today had not been developed much yet. So this was truly remarkable, okay? So you should never judge those great people's achievement from today's perspective, because today, a 10 years old can use equations. By that time, equation was a very new thing, okay? So what did Gauss do with this problem? He observed that if you combine one with the first one and last one, you get 101, right? 101. But because this sequence of numbers just increase in such a way that every time you just get one more. So the next number 2 can be paired with the second to last number 99. The sum will be once again 101. Why is that? Because 2 is 1 larger than 1. On the other hand, the 99 is 1 less than 100. So this kind of 1 is 1 bigger one, the other one is 1 smaller. They happen to cancel each other. So 2 plus 99 will be once again 101. And this process can be repeated until you exhaust all the numbers in the sequence. And right in the middle, you get 50 and 51, which perfectly pair up to get another 101. So this summation can be easily written as 1 plus 2. Let me make sure, yes. Plus 100. You can pair them up. 1 plus 100 plus 2 plus 99 and plus plus 50 plus 51. We have not changed anything. But why we are unable to do this? This is obvious to us, but mathematically it actually involves 2 very important rules. That's called associative property or associative law and commutative property or commutative property law. We will discuss that officially in a very rigorous way, or not, I would say very rigorous way. Certainly more rigorous than AOPS. I'm not making a jab at them, but that's true. So we will be able to reorganize, regroup those 100 numbers into something like this. So each one will be 101. And how many pairs we have? Obviously, we have 100 numbers divided by 2. We get 50 pairs. So we get 50 of 101 add up together. That would be 50 pairs. So therefore, we know we can do multiplication. So we will easily get this as 5050. Most people, most students learn this trick at a very young age. But this problem is so interesting is that we will be able to see in today's lecture and the next week's lecture how we can take a different look at the same problem. And that will give you a very interesting way to unite multiple different, seemingly totally different areas of mathematics, even at this very early stage of your mathematical study. So even this problem in its current form deserves a lot of attention. First of all, is this pairing really that easy to do every time? What if, say, I remove the last one? I will now ask you to just do up to 99. In fact, some people actually prefer to do that even if they do have 100. Why? Because 1 plus 100 give you 101. That's a little bit uncomfortable, right? Everybody loves a perfect number like 100. So even if you add up to 100, maybe some people will think, no, I will add this number separately. I want to pair 1 with 99. Why? Because it gives a much better number. It's 100. I love that. But there's a big problem. And what is that problem? When you have 99 being a pairing partner, you only have 99 numbers, right? Can you make perfect pairs without just too much investigation? You can see that No, because now you have one less number, so there's another number you cannot pair up. And what is that number? Well, it's right in the middle. What is that right in the middle? 1, 2, 3 to 99. What is that number in the middle? It's 50, right there. 50 is right in the center of the sequence, new sequence from 1 to 99. So if we do just pairing with 99, change everything to 99 here, and this will be 98, and so on, then we can see that the last one would be 49 plus 51, get 100, and then we have a 50, which is standing there all by itself. What does that mean? Means that our pairing process now becomes much less desirable. Remember previously we had 50 pairs, now we have what? 49 pairs plus 1 just left out. 49 pairs of 100. Now we have a separated 50. You have to add that 50 separately. If you did start with 100, meaning that you have to add 100. Of course, the result will be still the same because this will be 4900 plus 50 plus 100. Eventually, you still get the exact same number, of course. But when you do pairing like this, the 51 is always something you have to take special care. And that is a big hassle. So this pairing process actually has a big problem. That is that before you can even do any pairing, you have to count how many numbers I have in this sequence. Is this a kind of so-called even number? For those of you who have never heard of what is an odd number, what is an even number, it's just like, let me just explain quickly. Numbers like 2, 4, 6, they are called even numbers because they are multiples of 2. And of course, on the other hand, 1, 3, 5, 7, which are not multiple of 2, they are called odd numbers. Most people know this, but I don't assume anything, okay? So, if initially we only have an odd number of numbers in this sequence, do we still want to do pairing? Yeah, in this case, because we start with 1, it's quite easy to verify. But imagine if we have a different kind of starting point. Let's just say we have a sequence like we start with 35, 36, all the way say to 188. Can you tell how many numbers in this sequence? Yeah, this involves another big topic called counting, which is also important in middle school and high school math competition. We will discuss all those later in this enrichment program. But if I give you a sequence like this, the Gauss process will still work. It's just that the same principle, you can always, if there are even numbers in this sequence, you can always pair the first one with the last one, the second pair with the second to the last, which is 187, do this process. But whenever you do that, you have to be concerned with one question, is that how many numbers I actually have in this sequence? Can I do a perfect pairing? If it's actually an odd number, there is always a middle one right there making the big hole. You have to find that number and add it separately. And you have to do some unpleasant thing. You have to subtract that one from the total count, then divide by 2 to get number of pairs, right? We don't want to do that. We want a better solution. And what is the better solution? Well, in the original, if you look at this story, which I took somewhere directly from website, copied, excuse me, you can see that there's a trick of make the problem we just discussed, make it go away. And that trick is that now we want to do a fabulous trick, that is, we want to add the same sequence twice. Which hold you a question, why we want to do more work? You will see easily. If we want to do this sequence, make 2 copies of it, but reorder the second copy, in particular, we want to, instead from the first one to the last one, we want to rewrite the second copy of the exact same sequence from the last one to the first one, like this way, plus 1. If we want to add both copies up together, what will we get? Now, with the associative and commutative laws we mentioned but have not fully discussed, you can see that you can reorder the order of the summation anyway. So in this case, because we have 2 copies, we will be able to order this way. Pairing, this is exactly what we did earlier, but now 1 pair with 100, this guarantees that doesn't matter how many numbers you have in the sequence, whether it's 99 or 100, this pairing will always work, right? Let's just assume if, for example, this is not 100, this is 99, right here, then you will pair with 50 in our previous case. Of course, now that's a different issue because we do have 100, but the idea goes, it doesn't matter how many numbers you have sequence. If you pair them this way, this will guarantee everybody will have a partner or happy with a good friend to pair with. So, in the earlier example, say if it's 1 from 99, you will see that you will be able to pair everything. And that earlier, the one who had no partner to work with now just have itself. This is a twin brother, right? Because you got 2 50s in the 2. So once again, it can be paired. So if we do that, you can see that now the sum is just 1 plus 100 because we have 2 copies of the original sequence. Now the total pair will just be twice as many. Or to be exact, you start with how many numbers in the sequence, you end up with how many pairs after such a trick, right? So in this case, we have 100 pairs. And what will we do? Remember now, this result is not the original result we wanted. Instead, this is twice as many as what we wanted because we are adding 2 identical copies of the same sequence. So this sum is twice the result we needed, so we have to divide it by 2. And that gives you a perfect result. Exactly the same, but now we don't have to worry about earlier question, will pairing be broken? No, this guarantees that the pairing will work. So what is this new way to do things? Now observe 1 is the first number and 100 is the last number, and it multiplies 100, and what is that number? That's exactly how many numbers you have in that sequence. And that's easy to tell, right? Because now every number will be pairing with a second copy, a number from second, but just top down got reversed. So the number of pairs must be exactly as number of numbers in the sequence. So if you keenly observe this, we will be able to tell a general formula, say, if we plus 1 plus 2 plus all the way to n is a number. Now we switch to our algebraic notation, right? N is just a representation of an arbitrary number, an integer, positive integer. It can be 100, it can be 1000, or it can be just 5, all right? If we are doing this pairing process tells you the sum must be 1 plus n, which is the first one and last one. That's how we just pair them together, right? Multiply n, that's the total number of pairs, but we have to divide that result by 2. Okay, so this is the well-known formula for how to add from 1 to just a big number. Okay, this formula is so important that if you have never heard of it, I want you to spend 5 minutes before dinner time, repeat it, tell your parents, 1 plus n times n divided by 2. 1 plus n times n divided by 2. Before they yell at you, get out! I get it now. Stop. Do that. And I'm not joking. All right, so this is a very important formula. But when we study math, we always want to think about a little bit further, because this has a serious constraint that we have to start with 1. What if we do not start with 1? Let's just say we start with 37. Let's just say we add up to A1, A4. The beauty of this formula is that it still works. Just carefully observe what happened in this case. All we did is to make an identical copy of the same sequence. The second copy, we reverse it, and then pairing everyone in that new sequence with the first sequence, and then count how many pairs, which we know is the number of the numbers in the sequence. So this actually doesn't matter whether the starting point is 1 or not. The same principle applies, right? Because that's just 37, because 37, 38, all the way to 184. In this case, we reverse from 184, 187, all the way back to 37. We see that they are so perfectly aligned, we can still do the exact same thing and do the same trick. So this formula actually applies. So, but in this case, you need to plus 37 to 184. The next one is a small question mark. How many numbers in this sequence? If you have learned a little bit about the counting, you will know for things like this, it's 184 minus 37 plus 1. This is how many numbers you have in this sequence. Well, we will not officially discuss about counting, but we will in this series. But for now, you will see that you don't have to remember this. You just remember this is the total number of numbers in this sequence. And then you divide it by 2. The same formula will apply. All right? So this is actually beautiful. But we can further extend what we have studied here. Okay, let's do a few very interesting generalization, okay? We promise that in today's lecture and next week's lecture, we will exclusively work on this problem to see how many interesting ways we can discuss this. Now we switch to geometry. Again, we don't assume anything. We do not assume all of you have learned some very, very basic geometry stuff. And it's weird that nowadays everybody learn those things at an early age without truly understanding what they are. In my view, it's a pretty bad curriculum that was designed this way, but it is what it is. So what are we doing here? We're looking at some very basic geometric figures and learn to how to do something called area. Trust me, area is actually a very deep concept. It's way more difficult than what you see and what you have learned. In Euclid's geometry, just classic elements, that's what they essentially did more than 2,000 years ago. The Greek mathematicians used geometry to study numbers. But that's a long story, it won't be told today. What happens is that take a hard look at how we do the area calculation for those familiar To some of you, at least familiar figures. If you never heard of those things, don't worry. We will briefly discuss them, but they are not that difficult. Let's first look at a rectangle. This is a rectangle, right? What is the area formula? The area is B times h, where B is the length of the base, where h is the height, right? This area formula is so easy. Why I say that area is complicated thing? Because this is a geometrically idealized thing. In your case, everything must be a perfect integer, right? Like 24 times 5 and so on. Well, what is 24 times 5? That's 120. We know how to do that. But I tell you, b is not an integer. Like b is pi. We just discussed pi yesterday, didn't we? If b is pi, what is pi? Pi is a bizarre number. It's called irrational number. 3.1415926 dot 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 dot. It never ends. If you continue, this sequence can rapidly erase around and still cannot be down. It just goes on forever. Okay. If h, let's just make it as simple. Since we unfairly make b so complicated, let's just say h is 2. What is this number times 2? How do you do the multiplication? Well, we do know how to do multiplication if pi is finite, even say very long. If this is a number, let's forget about the decimal point for now. If we have a big number like this, we know how to do 2. We start with unit digit 12, carry 1, 5, and so on. We get that final result. But how do we do pi times 2? This number does not even end. We cannot even start. Where's the unit digit? So what is exactly pi times 2? How do we know when carrying will occur? Because sometimes say, look, when you do 2 times 9, you know there's a carrying. That's only because you work backwards, right? You work from the least significant digit, which means the unit digit. But in this sequence, that doesn't even stop. How do we know what numbers in the future are there? How do we do carrying? This is a very, very difficult, serious problem. If anybody told you, oh, in this case, the area is just 2 pi, that's only because that person deliberately did not choose to explain. Maybe that person did not understand what this is in the first place. How do you do 2 times pi? Think about it. It's not that easy to answer. For example, there are many digits there. How do we know what happened there? If you have to say, yeah, if we just do this, probably we can write this like something like 6.2. There's a carrying here, 5. This must be, say, 318. If we only do this. But what do you know about the future, the carrying? You just simply cannot write this down. Even you know 2 pi would be also an irrational number, it never stops. What is it? How can we even do multiplication like this? Well, that's a very serious problem. So, long story short, let's pretend we do not have this problem. Let's just say pi times 2 is just 2 pi, all right? Okay, this is the area formula. Area is a big deal, trust me. How about parallelogram? Well, the standard trick is that the formula will be exactly like a rectangle. Why? Because we can cut off this triangle and shift it to the right-hand side. In other words, we can cut and paste to remake a parallelogram into a rectangle with the same base. Essentially, just shift the base toward the right, right? Because this rectangle will make up what is missing on the right-hand side. You can see that this small piece will be moved toward the right. It just rearrange it. You still have the same base, same height. Excuse me. So the parallelogram area formula would be exactly looks like a rectangle. Okay, how about a triangle? A triangle case is a little bit more interesting, requires a little bit more creativity. You have a triangle here. what happens is that you can, just like what we did, and that's what we'll talk about. You can make a different but identical copy of the triangle, rotate it, and patch the original triangle like this. And it can be proven, of course, you learn this trick, but you do not do serious geometrical proof. That's what we will study in free Asian math later. By the way, free Asian math geometry will be much more rigorous and advanced than even you will learn in high school in America. Because in this country, they don't even teach you serious classic proof. They will teach you something called two-column proof, which is ridiculous. Okay, so you will do triangles area based on base, which is the length of the base, the height, base times height, then divided by 2. Why divided by 2? Because you have another copy which made it a parallelogram, right? This is a parallelogram with the same height, same base. So when you do triangles area, you don't do it directly. You first double it, then divide it by 2. Once you double it, you convert it into a rectangle. Therefore, you can use the already established area formula for parallelogram, b times h, but you have to compensate the earlier doubling up. So you divide it by 2. That is the area formula for triangle. And the trapezoid, finally, is exactly the same thing. Not exactly. I'm exaggerating a little bit. Almost exactly the same thing. How do you do the area formula for trapezoid? Well, you make 2 copies, right? Just like a triangle. You have a trapezoid here. If you don't know what is a trapezoid, well, just take a face value. Something like you have parallel lines. So you make another copy and turn it upside down so that it can be patched with the original one. Once again, it's just like a triangle case. We patch 2 copies of the same trapezoid, turn one upside down, patch with the original one, we get a parallelogram. So what is the base of this new parallelogram? Because this is just upside down copy of the original one, so this must be the top of the original one. Now we see that we will get this formula. What is it? You add the top and the bottom, a plus b times h divided by 2. Because a plus b, the top and bottom, add up to the base of the new parallelogram. That we kind of rolls back to what we did with triangle. Didn't anyone notice that actually the triangle case is just a special case of this version of the formula? You think about it, what is a triangle? A triangle can be considered a special trapezoid whose top is 0, right? Indeed, if we extend this trapezoid, the 2 sides, it will be converted into a triangle. So just adding a little bit of imagination, imagine a triangle is a trapezoid where top, the length of top is 0 because you only have 1 point. Remember yesterday we talked about what is a point? Point has 0 length. It has no dimension actually. So a triangle is just a trapezoid, but with the top, which here is A, where A is 0, A plus B, of course, A is gone. Clearly that reverts back to B times H divided by 2. So a triangle is just a special trapezoid. All the same, it's not too difficult to understand what is going on with those 4 basic geometric figures, how to do area. You were just told to memorize those things, right? So there are a couple of issues here. We do not tell you what if the numbers are not perfect integers, how to interpret that. But you take a face value of that. That is okay. But what are we doing here? What does this have anything to do with Gauss' problem? if you take a close look, what is that? That's exactly the Gauss problem. Why did I say that? Remember what we do? 1 plus n times n divided by 2. If we do not start with n, let's just say we start with a number a. It could be any integer. It doesn't even have to be integer actually, but for now, for simplicity of our discussion, let's just say we start with a number a. We get a plus 1, a plus 2, all the way to the last number. In this case, we do not represent something like a plus 100 or a plus 98. We just simply say the last number is b. Okay? A plus 1, a plus 2, blah, 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 until another b. Remember how we describe how this should be done? We said that you should add the first number, a, plus the last number, times how many numbers in this sequence? Well, if you know how to do counting, once again, the total number in this sequence would be b minus a plus 1. We'll study that, but for now, you just take face value. But why don't we call this complicated animal, give it a new name? We like simpler names, right? We just call this number h, which is the count of the numbers in this sequence. And in that case, remember what the formula is? The first one plus the last one times the number of numbers in this sequence. And we now know this number is b minus a plus 1, but we call it h. And that is h, right? Now we divide it by 2, just like here. That's exactly what happened. What is this animal? This is exactly the area formula for the trapezoid. Right here. Right here. Is that a coincidence? Absolutely not. Imagine what we did to derive a formula like this. Okay, let's just work on this number. What we did is to make an identical copy of the same sequence, reverse it, and pairing the second sequence with the first one, because we reverse second one, so we can perfectly align everyone with the number in the first sequence. But we did it horizontally, right? Now let's do that in the vertical way. Vertical. Big deal. And instead of writing those things in abstract in level, let's give some serious real numbers. Let's just say we start with 5. 5, 6, 7, 8. Let's not do too much. Just do 6, okay? Maybe 7. Like 7. 7 is always a good number, means luck. In Western culture, right? In Chinese culture, we like numbers like 6, 8, 9, just not 7. But we're not talking about cultural difference today. So let's just make it 11. 5, 6, 7, 8, 9, 10, 11. Remember what we did? We make another copy, turn upside down in this case. So we start with 11, 10, 9, 8, 7, 6, 5. We add them up and then divide by 2, right? Did you see how similar to what we did for the trapezoid? In the trapezoid area calculation, we just did this 5 minutes ago, right? Did you see that those two things are actually exactly the same concept? Not exactly the same thing, but exactly concept. We turn identical copy of a trapezoid, turn it upside down, patch it. If you think this patch is actually just a pairing, you can say that. So we pair the second trapezoid with the first one. What do? We get a parallelogram. In this case, parallelograms top and base, of course, are the same numbers. Isn't that just 5 plus 11? And the bottom is 11 plus 5 right here. Most interestingly, the property of parallelograms is that if you make all the cut everywhere, you get exactly the same length. The cross-section length must be exactly the same. And that is exactly what happened here. Right? So the two tricks are actually exactly the same, except one is in arithmetic and one is in geometry. In fact, if you think about this way, you can even, without just paying too much or being too much troubled by the tiny details, if you can think about this trapezoid, let's just this trapezoid. The top is 5 and the bottom is 11. You cut them into 6 pieces. Approximately every piece can be just made like this. This is the average length of this first piece is 5. The second piece, the average is 6. The third piece, average is 7, and so on. And you are doing the area. It's exactly what happened right here. Okay? So, what we are trying to explain here is that this geometric trick of generating the area for trapezoid or triangles is exactly the same trick how we solve the Gauss summation problem. If you have not been impressed, either you are too smart, because this is nothing that can surprise you, or you are too insensitive. How about that? All right, so let's jump to another way. We'll skip this slide because we are running out of time, and this can be perfectly discussed on another day. Generalization of this problem into a so-called arithmetic sequence. So we'll skip this. Let's talk about one interesting problem. We will take a fresh look at the from a totally different angle into exactly the same problem. Give you a wonderful. Is everybody bored already? We are more than 1 hour into our. We only have about 13 minutes, but we will see. Maybe we'll extend it. We will take a fresh look at the same problem from a surprising angle. I promise it will surprise you. Okay, so what is the problem? Let's just say this year, the NBA has changed their rules because last year too many injuries, right? All the superstars got injured right before playoff. They play too many games a year. They play 82 games before the playoff. So that's a long, exhausting season. But more importantly, a lot of good players got injured. NBA said enough is enough. Let's change the rule. For this year, they decide all the 30 NBA teams will only play a so-called single round robin tournament as the playoff qualification season. Everybody knows what a single robin, right? Round robin, right? Meaning that you play every other team in a rotational way. So 30 teams, each team will play against any other team and all other teams exactly one game. And see how many games you can win, rank you, and set up the seeding for the playoff. Let's just assume NBA is doing that this year. So all the 30 teams play a single round robin against each other to qualify for who can go to the playoffs. The question is that how many games in total will those teams play? Does this problem have anything to do with how we derive the Gauss summation problem? Obviously not. What the heck? What does this have anything to do with the Gauss problem? Or more interesting, how does this have to do anything with how to calculate the area of a trapezoid? You must be crazy. Well, this is why math is so fabulous. Okay. Let's think about what is round robin. This is a simple lesson 19, right? You just play with each other. You count how many wins. You just play one game against each other. This is actually a classic counting problem. Okay, we keep talking about counting. Why counting is important? Because if you want to do competition math, AMC, IMO, or ultimately IMO International Math Olympia count is one of the 4 subjects that you have to study. But more importantly, if you want to go to computer science department in college, this is a very, very important area called discrete math. Everybody needs to study that. So it's good for you to learn such things that school math will never teach you before college, right? In high school, you won't even know this. So let's consider this problem. If you have 30 teams in a tournament, how many games you will play in total? Well, this is a counting problem. There are 2 ways to do this. Okay? How do we do counting problem? Well, we will talk about this later, but today, because we run out of time, we'll directly jump to the substance. Let's just count, shall we? Let's just say start with Golden State Warriors, which is my home team. I live here, right here in Silicon Valley. My Warriors just won the 4th title in 8 years, beat all of you guys from any other teams. So, eat it. Your team lost. Go Dubs. Okay, so Golden State Warriors is just one of the 30 teams. How many games will Golden State Warriors play? How many? Well, it will play against every other team, right? So it will play 29 games. Okay, so we already count how many games Warrior will play. Now let's consider next team, Sacramento Kings, which is the closest team to the Warriors. Remember, we are trying to count all the teams played game. So how many games will the Kings play? Well, the Kings is logically in the same situation as the Warriors, so it also will play 29 games. Can we count King as 29? Well, if you do that, you just commit a mathematical crime in its worst form. Why? Because remember, this is a single round robin. Every team can only play with each other for exactly one team. It doesn't matter who is the host, who is the visitor. Between Warriors and the Kings, they can only play one game. And that game has already been counted in Warriors count. So when we now count the Kings game, we cannot take that one. Cannot count it twice. So we will remove that game from the number of games that the Kings will play. How many new games that in this counting, for this counting purpose, will Kings play? Must be 28, right? Because Kings is the second team we are now counting. So, but we cannot count that very game that it played with Warriors because we already count Warriors. So the King, for our total counting purpose, has 28 games to contribute to this total count. By the way, none of those 28 games has already been counted in Warriors game, right? Except that one game between Warriors and Kings. All the other games has nothing to do with Warriors, so we will count the Kings game as 28. It's not too difficult to see that this argument will continue. Maybe next game will be Forever Sox Clippers. By the way, they are rumored to have the best chance to win NBA the title next year. But they've never done that, right? So, how many games will Clipper play, but that has not been counted in either Warriors count or the Sacramento Kings count? Must be 27, right? It had 29 games to play in total, but we cannot count either the game against Warriors or the Kings. So for Clippers' purpose, it will only contribute 27 new games in this total count. And this argument continues until let's just have two teams left. The last two teams, they only contribute one game exactly between themselves because against anybody else's game has already been counted. And after that, you only have one team left. This team has no one to count because all the games it played has been counted by the first 29 teams. So after rows, the last team standing, it has no new games to contribute. Therefore, the total games rows 30 teams play will be 29 plus 28 plus 27 plus da 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 plus 1. Okay? Of course, there's a total, but we don't do that. Everybody convinced? If you're not convinced, even I was silly, I did not do a good job, or you are playing video game. Because I explained it in the most perfect way in the world. If you cannot understand it, it's not because you are not smart, because you are playing video game. And it's not because I'm not, well, maybe I'm a bad teacher. Okay, anyway, this must be the total games those 39 teams played, right? 1 plus 2, if you reverse the 29 plus 28 plus all the way to 1. What is total? We don't do that for them. So that's the first way of count this. How to count this? Let's think about another way to count this. Didn't we just say that when we start with Warriors, it will play 29 games? Why did we generate this in the first place? Because we don't want to duplicate games. For example, in the Sacramento Kings, when we count the Kings game, we cannot recount that game it plays against the Warriors. So we have to reduce that one. But let's just forget about that temporarily for now. Let's just count everyone without this kind of duplication. How many teams we have? 30. How many games each team will play? 29. A naive thinker, our total is 29 plus times 30, right? 29 games each teams will play, and 30 teams. Yes, my second grade teacher taught me that you just do multiplication. That's a no-brainer. But that's one big problem, right? Like we explained, in that case, the game between Warriors and the Kings will be counted twice, and exactly twice in this multiplication, right? It's being counted as a Warriors game. It's also counted as a Kings game. Both teams counted. So this has been duplicated once and exactly once. So each game is counted twice. But other than this problem, is there any kind of just duplicated counting? Nope. That's the only problem. As a result, we can solve that problem by compensating the problem. How do we do that? Because each game is counted twice, and exactly twice, and everything else is cool. We just correct this problem by dividing by 2. You think about it. This is exactly how many games those 30 teams will play in a single round-robin tournament. 29 times 30 divided by 2. Why we are doing this? Compare the first number in red and this second number in green. What can you conclude? They must equal to each other, right? Why? Because this is the physical fact. This is the total number of games all those 30 teams will play in the single round robin. You cannot change that. Even Albert Einstein cannot change that. Even President Joe Biden cannot change that. And certainly Vladimir Putin cannot change that either. Maybe Steph Curry can change that. I don't know. Because he's Superman from another planet. Who knows? Okay. We just did extraordinary things. And what we did? We counted the same problem from 2 completely different perspectives. But we are doing exactly counting the same thing. So they must equal to each other. So we just proved 1 plus 2 plus 3 plus all the way to 29 equals to 29 times 30 divided by 2 without doing anything, without thinking about anything. But you observe this is exactly the formula we discussed earlier in the Gauss case, right? 1 plus 29, the first one plus last one, times how many? 30 times total number 29 divided by 2. Under the Gauss calculation, this is the formula we just developed. But we went through a process like what we saw in the trapezoid area calculation. We have to make another copy, turn upside down, combine everything, times the height, and blah, 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 blah. We get this formula. The first one plus last one, 1 plus 29 times total, or the height of the trapezoid, 29 divided by 2. Yeah, that's cool, but what did we get here? Of course, they're exactly the same thing. But this is just a counting interpretation that has nothing to do with that silly trapezoid argument. That's just so dumb. Why did you do that? I can do a much smarter way without all the labor, right? 30 teams, each team play 29 games, 29 times 30, but there's a overcounting problem, but that can be easily fixed by divided by 2. That's it! I got exactly the same formula in a much, much smarter way. And so what? So what? Have you not been impressed yet? If you have not been smart yet, you promise to anybody, especially your parents, you will go to International Math Olympia one day, right? Because you are genius. Nothing can surprise you. Come on. So, what we did actually in this particular case is what we call a bijective proof. Let me write down that term for you. It's called bijective proof. This is especially fabulous in combinatorics. You essentially count, facing a counting problem. You counted in two seemingly completely different ways, but it's the same problem. Your final count must be the same, so when you count it in two different ways, you get a result. And that result won't change, doesn't matter how you count it. You count it from first one to the last one to the first one, count starting from middle, go back to Sacramento, go to Las Vegas, then come back, you count everyone must be still the total, same total. So, but along the way, you prove something must be equivalent to each other because they all give you the same result, and that's called bijective proof. And that generates exactly what we just got, either from the Gauss way or from the geometry way. That's exactly the same result. And this is the beauty of math. I will see you next week. All right? Bye, everyone. Have a great weekend. Bye. See you next time.